Okay, so it's the ratio of concentrations. Yesterday we had those graphs, and I said the products were on the top graph, on the the line stretched to the top of the graph, like this, and this top line was product concentration, and this bottom line that came down was reactant concentration. I said that the reaction favored the products, right? What did we say about K? Is it greater than, equal to, or less than 1?
Greater than 1.
Why was it greater than 1? You're making the what bigger? The products, which is the numerator, right? So if the numerator is the larger number, that makes the overall fraction greater than 1. Math makes sense to us, yes? I'm not a math teacher. All right, so that's what, when the products are favored, you would say K is greater than 1. So it tells you which side of the reaction is favored. If you know K, let's say K was 1,000, what would you automatically say? It's favoring the products. If I said K is 3.8 times 10 to the negative 4th, you'd say it favors the reactant. And then there's this other situation where K is equal to 1, it favors neither. It favors neither one specifically. Okay, so I told you yesterday the pure solids and pure liquids, we do not include them in our Ks. And I'll go through an example to actually show you that what the heck that means. Can I go? Thank you, I like this. Okay. So we've got gas, gas, gas. Pure solids or pure liquids? No. Okay, so I can include all of these in my K. When I write this one, I'm going to do the first one for you, and then we can do this one together. This is my product, right? So I'm going to say K is equal to concentration of products. My concentration of NO. What's the name of NO? Nitrogen monoxide. Okay, so nitrogen monoxide, that 2 goes where? Exponent, right, over the concentration of both of these, but we don't add them, we multiply them. So we're just going to say concentration of nitrogen to the first power, and I can put a 1 there just to remind me of myself, and then O2 to the first power, because their coefficients are 1 and 1. It's really not hard to write that expression, as long as you know it's products over reactants. And then I can give you values, and these, remember yesterday, I don't know if I actually put the EQ on it like that. Did I just say KEQ yesterday?
Yeah.
So EQ represents what again? Equilibrium. So this is the K expression. These are concentrations at equilibrium, which means that if I know the concentrations at equilibrium of NO into NO2, I can plug in values. And if I can plug in values, I can solve for what? If I can plug in a value for this one, and this one, I can solve for K. And if I can solve for K, I can tell what about the reaction. But it's favoring. I can tell if it's favoring the product formation or reactant formation. I just have to know the value of it, right? If it's greater than 1, I say products favored. If it's less than 1, reactants favored. So I can solve for K, and I can determine the favored side. So once I plug something in, I can do all of that. It's kind of nice because it's an easy expression. All right, look at this next one. What do you notice that I cannot include? Which one? Which one? I see a gas, right? That's not pure solid or liquid. We're cool. I see aqueous. That's not pure solid or pure liquid. I actually have to say L for it to be a pure liquid. And then I see a solid, right? That's a pure solid. So I cannot include that in my equilibrium expression. So I'm not going to I'm going to kind of ignore it, but I'm going to put a 1 in place of it. Okay? So K. Say K. Okay. This right here, I would like to put in the products, right? But I can't. So I just have to put 1 up there. But I can put these other reactants in there, that's fine. So concentration of NH3 to what power? 1 times concentration of HCl to the 1 power. So it looks weird because you're not including that right there, but that's okay. Yeah.
So if it was like this of pure solid and liquid on the other side, you just put a 1 on the
Yeah, you can put a 1 on the bottom and that's fine. Yeah.
So the chlorine is a solid, but why would you not use the
It's because this entire thing is ammonium chloride and they stay together. So that's an ionic compound and you don't get to separate it here. They have to stay together. Yeah.
why is it pure?
It is a pure gas, and that's fine. On our exceptions, we could only exclude pure solids and liquids. And that's because, like, how do we get molarity? What are the units? Moles over liters. Can I have, in pure water, guys, can I have so many moles of water over so many liters of water? It's going to be the same thing. It's pure. It's going to be one all the time. So whatever my moles of water is, it's in the same amount of liquid water because it's the same thing. So it's like we actually cannot find the concentration for pure anything. Because it's not like, oh, I've got so many moles over this big liter. It's the same exact thing. So you can't actually find molarity or anything that's pure. Gases are different. They create pressures. Their concentrations, we actually call them partial pressures, and they're just a teeny bit. All right, so speaking of pressures, actually, let's do this first. All right, you guys have 6 minutes, 6 questions. I want you to write out your K expressions for these. I'm going to make it a little bit. If you need to move around some, but just on your own paper. So I can't read my book. I can't read it. Oh, these type of pictures. This is for 3 years now. 3 years. You can raise it to the power of 2. Yeah, don't put it within it. Just put it as an exponential. First 3, okay? Anything you've excluded yet? Anything in number 1 you excluded? No. Number 2? What? The carbon solid. Good. Number 3? Or actually the C, or this one, I can't actually talk right now. Carbonic acid's fine, it's aqueous, but it's the liquid water that you will be excluding. Right, keep going. Alright, I'm going to go to my chicken scratch answers right now, and then I'll flip back and forth. So the hardest one was probably number 5. We got 1 for number 5. Yay. Alright, so we see that in number 5, I'm going to go back and say to number 4, solid, liquid. All those have to be excluded. So like we said, we replace it with 1 anytime we exclude it. It'd be 1 over 1 times 1, it's 1. So those are sometimes kind of awkward. That means that this has neither side favored. Number 4, whenever you guys wrote it, you saw that you had ions already. Those ion charges have to stay within the brackets, but you've got to incorporate the 1 and the 2 as exponents. So looking at number 4, it's just magnesium to the first, or magnesium 2 plus to the first power, and bromine to the second power. Over 1 if you want to, but over 1 doesn't mean a whole lot, so you can just exclude that as well. Number 6 is all sloppy. Here, rewrite that top part. We've got, what was it? H3O plus and acetate, thank you. Over acetic acid. Questions on any of these? Excluded water. I want to talk about these reactions real fast. So back here, this is just a, what kind of reaction is number 1? What of our 5 types? Decomposition, right. So we have one reactant, we're making multiple products. So that's a decom. It doesn't get a special ending, so we just call it equilibrium, KEQ. And so whatever you have equal to, say KEQ equals whatever you put down for that. For the next one, what do you see? It's kind of like a single replacement, but it's gas formation. It doesn't have like a special type of name. So I'm just going to call that one KEQ as well. This one is what? Next one, 3. That's synthesis, right? So we've got 2 things coming together as 1. That one for us, for equilibrium, we just call it equilibrium. It doesn't have a special name either. This one has a special name. Okay, so what this one is a solid dissolving into 2 ions, or more than 2 ions here, in aqueous solution. So we talk about solubility of solids in aqueous solution. We have a special name for this one. It's called KSP. SP stands for solubility product. So if it relates to solubility, like ionizing in solution, we call it KSP. We're going to go over that one extensively on Monday. The next one we see is decomposition again. It doesn't have a special name for equilibrium, we just call it KEQ. What do you see that's different about number 6? We talked about this last unit. It's what? It's an, what is that? It's an acid, acetic acid, right? So this is an acid, and that would be acting as the base, reacting to form, this H plus is coming off to form hydronium, and it's almost neutralization. It does make a form of water. It's actually reacting with water. This is called the acid dissociation reaction. It's just acids reacting with water. That's an Arrhenius acid, so it's acting. How does it act in water? It's making hydronium. But this one has a special letter that we put with it. We call it Ka. Remember we talked about Ka last unit? I said Ka meant something with acids and Kb meant something with bases. So give me an example of a base. HCl is an acid. LiO, or out of water, can actually act as a base as well. Lithium hydroxide, I'm not going to put with water, will create lithium and hydroxide, and you can write a Kb for that one. So sometimes these letters mean something because it's representing the reaction. Sometimes they're just equilibrium, so you don't have to worry about it. I say that because that's the next thing we're talking about, y'all. I'll come right back to that. All right, so there's a couple different types of equilibrium. Just write down homo means same state. So I'm trying to let you read notes and see that it's really, you don't have to write down everything. Homo, same state. So when I say same state, I mean they're all gases, they're all aqueous, they're all solids, whatever it is you think that you're writing. Most of the time, it's going to be gaseous equilibrium that we're discussing. Hetero means different states. That's pretty easy. So, different states. Don't forget that you will not be including the pure solids and pure liquids if they are within that BCE. So, you don't even have to write this down because you kind of already, we've talked about that a lot, you wrote it down before. So, just write homo, same states, hetero, different states. Usually that means you're going to have to make sure you verify that everything can be included. So, let's write down the equilibrium expression for lead 2 chloride. Go for it. So what do I write? I say K what? Ka, Kb, Ksp, K equilibrium. Right, so this is solubility again. You can see the ionization happening. Ksp equals concentration of Pb2 plus
One minus.
over what? Over 1, right? So I'm not going to write over 1 because it doesn't do anything. That's because that's a solid, so you don't include it. All right, cool. So KSPs, it's just they look different. They don't have a denominator, like ever, because they always have a solid making 2 ions, so the solid never gets included, so you never have a denominator in KSP ones. You're going to see that pattern a lot. So versus you waiting for you to see the pattern sometimes, I just like to tell you up front. Yeah.
What was that SK standing for?
Solubility product.
So as you know,
If you have a solid ionizing to 2 aqueous ions, that's how you pretty much will see it like that all the time. So KSP means solubility product, and that was in your reading guide. All right, the last thing here is just basically I'm going to give you an example of each type so that when you're exposed to it, you're not frightened. So gaseous, a lot of times you'll see it as KEQ, or you can see it as KP. What do you think the P stands for? Pressure, yes. Gases cause pressure, so that P means pressure. So all of the gases are pressures. All the gases can cause pressure. So I can't really measure the concentration of a gas very well, but I can tell how much pressure a gas causes. All I gotta do is find a barometer, and that's it. I'm good. So if I give you an example of N2, this was my example yesterday, equilibrates to NH3, balance it. There we go. This is gas, gas, and gas. Instead of just writing brackets, sometimes we might have to use pressures. So it looks just a teeny bit different. We're still going to do products of reactants though. We're still going to raise it to their exponent. So I'm going to say partial pressure. So P of NH3. See that's 2 right here for NH3? I still have to square it, okay? So it's not a box anymore. It's a parentheses. And we square it still. It just looks just a little different. So there's no more products, right? So over what? What do you think? Pressure of N2 to the first power, right? And pressure of H2 to the third power, right? So those are they're called the partial pressures. Partial pressure KSP ones. The K expressions. They're the same thing. It's just you have to write it with pressures if they give you pressures. And I'll talk about the meaning with this change in total pressure, no effect. I'll talk about that when we talk about another concept later. Aqueous, a lot of times you'll see it as KEQ, or if it's talking specifically about acids, you have to use it in Ka, or if it's specifically about bases, you use a KB. It's still the same thing. We're going to put products of reactants. And do you remember this one? Larger Ka means stronger acid, larger Kb means stronger base. Strong means what here? Ionizes more, 100% ionization. All right, so looking here, we have an acid, water, and I'm going to go ahead and put an L there for you so you know it's pure liquid water, and then aqueous ions over here. So what would be the Ka expression here? Concentration of H3O plus times concentration of X minus over concentration of HX. No liquid water, right? So ignore it. All right, look at my random KB here, my B expression. Looking at this one, what do you want your KB to be? This is still pure liquid water here. Of hydroxide times of HB, I hear you, keep going, of B minus, right? So water is excluded again. So still, products of reactants, we just call it different things, so don't be like, I don't know what KB is, because you really do. It's still the same setup. Alright, and then we'll go back to those 3 questions. Let's get them. And then, if this lab's good for us, I have this other example of KSP that you guys might really, really like. It's kind of sweet. I'll let you help me decide later. Okay, I'm going to do the KSP one when we do KSP on Monday. Oops, no, I missed the questions. There it is. Oh, I'm sorry. Okay. Okay, so read this question with me. Write this down. These are your 3 lecture examples of case. In gaseous equilibrium, 2A plus B equilibrates to 2C. The equilibrium concentrations of A, B, C are blah, 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 respectively. What is the value of K in this reaction? First thing I want you to do is always write the KEQ. What's the KEQ for this reaction? It's the concentration of the C to the second power over and times concentration of B. So all we're doing is writing it down from our BC. All right, now what do we want to do to actually solve for K? Plug them in, right? Plug in values. So KEQ is equal to, what was the concentration for C given?
1.5.
It's respectively, there we go. 1.02 times 10 to the negative 2 molar squared over what? 5.50 times 10 to the negative third squared that as well, yep, times B. So all I'm doing is reading the problem, plug in. And thank you. Have your calculators. I want to make sure you plug your calculator out, or plug it into your calculator correctly. For this, once I plug it in, I just put parentheses so that it's no longer, it's still representing concentration, but if I put the M there, I'm also representing, so it doesn't matter when you plug it in. When you write it out by itself, you have to do brackets. So in your calculator, parentheses 1.02 times 10 to the negative 2, and parentheses squared, divided by entire denominator has to be in parentheses or it's not going to be pretty. 5.5 times 10 to the negative third to the second power times 2.25 times 10 to the negative third in parentheses. What'd you guys get? Say it again. Try it. I think your parentheses are in the wrong, someplace in the wrong spot. So you absolutely, 1528. Okay, cool. 1, 2, 3. Mine's inside communication. Yeah. So I've got 1528. You else get that? All right. That means that whenever you plug in your calculator, if you want to, you can just plug that value in first and get what that is squared, and then parentheses. These both have to be multiplied by each other, and that one's got to be squared first, of course. Multiply by each other. Get that whole denominator, and then go back and divide. That's fine, but you've got to keep the denominators multiplied together. Anybody else confirm you got 1528? Thank you. If not, I will show you how to make sure you put parentheses in your calculator correctly. But that's just something I don't want you to I don't want you to know this and totally screw up your calculations so you can't work your calculator appropriately. Okay. So if you're good, you're good. I just want to go through one more of or at least both of these. Otherwise, we can set it up and we can solve it. All right. Methanol is manufactured according to the following equation. The equilibrium constant at 400 Kelvin for the reaction is 1.609. So that's what is that value representing? The K, right? So this is K. It says 400 degrees K. I don't really care. They have to tell us the temperature because K's change when you have different temperatures. Ignore the temperature. It's useless. The equilibrium concentrations are blah, blah, blah. What is the H2 concentration of the vessel? So what was the first thing I told you had to do? Write the K. Write K. So write K again for me. KQ is equal to? So methanol concentration over CO. So H2 squared, right? All right, so I don't know H2. That's what I'm solving for, correct? So I'm just going to call it X. We're going to solve for X. Yeah, we're going to solve for X squared, and then we'll solve for X by itself. Okay. So when we plug everything in, we say K is equal to 1.609. Concentration of methanol was 0.818. Concentration of carbon monoxide is 1.402. I don't know X because that's what I'm solving for. That's my H plus or H2 concentration squared. Gotta solve for X. Okay, but I have to pull x squared at the bottom eventually, right? Can I just go ahead and pull x squared at the bottom now? Let's go ahead and do that now. I have to multiply both sides by x squared, yes. Alright, I'm assuming that we're okay with the algebra. If you're not, come see me. So if I multiply x squared on both sides, that cancels them out on this side. Then I have x squared times 1.609 is equal to this mess. Go ahead and solve for this mess. Not over that. So 1.609 x squared is equal to 0.5835. Yeah? How do you solve for x squared? So divide by this, 1.609, divide by 1.609 on both sides. So that cancels out. X squared is equal to that divided by that. So 0.58 divided by 1.609, 0.3626, and then 0.6. That's what you got. Divided by that. Sorry. The root. So x is equal to 0.602, and that's also equal to the concentration of H2, because that's what it asks us to solve for. So if we put x in for H2, then that's exactly what we should solve for. Solve for x. Do not multiply by 2. Don't do anything crazy to it. Don't square it. We just substitute that in and solve. Okay? And then I don't know if I want to do this one. Let me double check. Oh, I do, unfortunately. Okay, because it's got the favorability. All right, the following equation represents the decomposition of phosphorus pentachloride equilibrates to phosphorus trichloride plus chlorine gas at 25 degrees C. Don't care. Okay. The equilibrium concentration of the substances are blah, blah, blah. What is the value of the equilibrium constant for this reaction? Are reactants favored or products favored? Do it. Should be done on your papel with your lapis, por favor. Answer? Let me know when you do. At least, what was the first step he did?
24.
I didn't get 24.
You got 0.04.
I got 0.04. Okay, so that means what's favored? Reactants are favored, right? So first thing you did was set up the KEQ, yeah? Oopsies. KEQ was concentration of what? PCl3 times concentration of Cl2. So both the products over the reactant, PCl5. And then you did what? Plug them in. Well, we have this and this. For both the products have the same concentration, 0.229 molar, 0.229 molar, or you could just done that squared, divided by the concentration for the reactant, 1.271 molar. As long as you multiply correctly in the top and then divide by your denominator, you get 0.0413. So definitely what? Reactants or products? Definitely reactants are favored. Way smaller than 1. Alright, so these aren't bad. These are the easier ones because I already set up the expression so that you just plug in your equilibriums. Tomorrow we're going to, tomorrow and Wednesday or Thursday we're going to work on some that are still a little bit harder where you have to go through a little bit more of a process to get to those values. But if you know this, you're solid, guys. This is stuff that it takes me 2 months to teach. This plus more, of course, in AP. So, you ready to catch yourselves? Catch yourselves. All right, and then we're gonna get to our lab. I'm gonna tell you about the lab first. Oh, this is what I might do if we can work hard. It's a KSP example. Oh, what have I done? Okay, this is what we might do if we can work through this lab very well. I mean, I sure hope so, because I'd like to eat them at the end, but we shall see. Okay, starch and iodine. What happens when you put them together? No, what do they turn? Purple. Think back to biology. That's where it's biology. Okay. Starch. You did the starch in a baggie experiment, maybe? Someone said it earlier. Just wait. What? Turns brownish purple. Okay. So starch is an indicator. I'm sorry. Iodine is an indicator for any starch. And you put it on a potato, it turns like deep dark purple. Sometimes it's kind of brownish in color. So what you're going to do is you're doing an example of this in the chemical terms, because it's an equilibrium reaction. But you are measuring the rate of reaction. You want to know how fast does this reaction occur. Well, if the reactants are clear and the products are purple, with me? If the reactants are clear and the products are purple, you have to time the amount of time it takes to make purple. If it makes purple, you have made products, right? So you're going to see the concentration change over the time that it takes to make that. And what you're going to do, I already have mostly everything back there. You have a stopwatch, you've got beakers, you guys go get your test tubes out. And when you guys store your test tubes this time, you know I've got like those little prongs on the other side of the test tube, right? You just turn your test tubes upside down. They'll stay in there better and they won't jiggle whenever you're trying to get it out and break the test tube. Graduated cylinders, you have everything. I'm going to have one hot plate and one ice bath per station, so all 6 tables, so we'll just share those. And then you have 2 solutions. The first solution has the iodate or iodine substance in it. It's clear. The solution B has the starch in it. Starch is like cornstarch kind of stuff. It's really blurry. So remember, B, blurry, is that's how you know, like if they're not labeled back there, if you turn around you see Jared. Jared, hold up the blurry one. So that one's blurry, and the other one is clear. So solution A is the clear one, solution B is the blurry one. Okay, put it back down, thank you. The solution B has acid in it. Please do not get it on you. Sulfuric acid is strong. Okay, and when you get to this part 2 of the lab where it says take 2 hot trials and 2 cold trials, just do 1 and 1, because we'll compare all of our data together. Okay, when you get to the math part, let me know. I will help you some, but I'm not going to hold your hand the whole time. Okay, you can make your own groups. Please remember, 4 people that got front station, 4 people back station. Grab goggles on the way back. Yes.